MICROSAR IO uses our lightweight service-oriented communication protocol to exchange data over the network. You want to know how it works? Then let's dive into it. Hi, I'm Florian, and I want to show you how to set up services in MICROSAR IO and how to communicate with other ECUs. We have developed a new lightweight service-oriented communication protocol for MICROSAR IO. The ECUs in this network are connected to each other via a bus topology. It is designed to have a minimal wire overhead and fit to simple physical layers like CAN or LIN. The exchange data is defined by services, which makes the configuration and the implementation very simple and readable. A service itself is a bundle of service elements. There are two types of service elements: methods and events. Methods follow a request-response pattern, where the client explicitly sends a request to a specific server, which then replies. Events, on the other hand, are sent by the server independently, without being triggered by the client. A MICROSAR IO ECU can be server and client at the same time, so we get a very flexible communication setup. To get a better feeling of how the service communication works, we will create a new MICROSAR IO project. But what project? I'm pretty sure that every programmer loves blinking LEDs. We will set up a service that will make an LED on the ECU blink. The service is requested by the client ECU, and the server ECU implements the LED logic and sends back the response. The development of MICROSAR IO, as well as the configuration of the services, is done in Visual Studio Code. So let's start VS Code, and we begin with our project. At first, we create a new service by opening the service interface model.yaml file inside the configuration folder. Here, we add a new service definition with a unique ID and a name. Then, we add a service element with the name enable. As service type, we want to use a method in our project. So we define the method request and add a new member element with a new int8 parameter to set the state of our LED. As response, we do the same, adding the names of the elements and add the uint8 parameter as our return value to see if the LED was enabled successfully. Great! We have defined our first service. The next step is to make the connection between definition and deployment. We open the service manager.yaml file to configure the service manager component. The service manager deploys all defined services to our specific communication setup. First, we deploy our LED service by adding a new element to the application service. Here, we set the ID and the reference to the service definition. This ECU implements the logic of the LED, so the role is server. This logic is triggered by the client ECU, and the client and the server must recognize each other. For this, we configure the deployment ID. Let's use 2000. Then, we reference the channels on which the service is sent and received. Finally, we set the TX confirmation to false because it's not needed right now. Cool! Our service is deployed to our communication setup. Let's continue with the LED logic. We open the application framework.yaml file to connect our service deployment with an application. I have already prepared the basics with an init and a main function, as well as the task mapping to trigger the service manager main function every 10 milliseconds. Making the link between application and service is super easy. We just add a new service reference to the application and set the reference for our LED service deployment. Now we press the build button to trigger the code generation of the application framework. The application is configured and generated. Next, we implement the LED logic. We go into the user code folder and open the generated application framework app.demo.c file. I have already prepared the basics, and at the bottom of the file, you can find the main function, which is called every 500 milliseconds to toggle the LED pins. The variable LED set state is used to enable the blinking of the LED and is set in the service implementation. To implement the service, the receive callback of the method LED enable is generated. Now, we can add our code to get the received state and write it to our global variable LED set state. This value is also used as return value for the client. For sending back the response, the API LED enable send response was also generated. And that's it. Implementation is ready, and we can build and upload the code to the hardware platform. Now, let's take a look at our hardware setup. I'm using a hardware board, which is connected over a CAN transceiver board to a VN box. I use this VN box to simulate the client ECU in Canoe. In Canoe, I have prepared a very easy simulation setup. It just contains the virtualized client ECU, which is connected to our CAN network. In the bottom right corner, we can see the panel to enable and disable the blinking of the LED. This panel triggers the transmission of the service frame in the right format. Now, we start Canoe and activate the LED. In the trace window, we can see the request of the client ECU as well as the response of the server ECU. Okay, let's take a look at our hardware. A blinking LED. I love blinking LEDs. Very nice. With this, we have successfully completed our project. And you can see how easy service-oriented communication works in MICROSAR IO. You feel the excitement and want to have your own experiences with MICROSAR IO? Get in touch with us and download your free evaluation bundle. The link is in the description. You like MICROSAR IO and our vector tools? Dive deeper into our products and tutorials by subscribing to our tech tutorial channel and hitting the bell for updates. Catch you later! Wow, I like MICROSAR IO.